Chapter 9 is on nuclear chemistry. So we're going to start off by talking about the difference between a nuclear and a chemical reaction. So we're going to do a little bit of review on chemical reactions. The first thing we're going to talk about is how we learned previously how outer electrons are involved when we do bonding. So for example, here I have an atom of sodium, and its outermost shell we have one valence electron. And in chlorine, its outermost shell has 7 valence electrons. And we learned on the octet rule that atoms and ions are most stable when they have 8. So this is what causes sodium to lose this electron, and it's transferred over to chlorine. And this is how sodium forms that positive 1 charge by losing the electron, and chlorine forms a negative 1 charge by gaining that electron. They both end up with 8 valence electrons, but it's the outermost shells is where we have this bonding occur. So this example, we have an ionic bond formed between sodium and chlorine. We also learned about chemical reactions. So in this reaction here, we have CH4, which is known as methane, plus oxygen, forming carbon dioxide and water. We have a combustion reaction. The thing I want to point out here is that in our reactants over on the left, we have carbon, hydrogen, and oxygen. In our products, we still have carbon, hydrogen, and oxygen. They've just sort of rearranged places to create new compounds. Now, nuclear reactions are different because we said in chemical reactions, it's those outer shell electrons that are involved. In nuclear reactions, they occur in the nucleus, hence the name nuclear, and they sometimes involve inner shell electrons. So, maybe these electrons in here and in our nucleus is where nuclear reactions take place versus a chemical reaction. And the other thing in a nuclear reaction is you actually create new elements. So if we look at this example down here, we have uranium-238. This is a radioactive isotope of uranium that's used in the nuclear bomb. Uranium-238 gives off a radioactive particle called an alpha particle that we'll be learning about. And when it does this, it actually creates a new element. So uranium decays down into thorium. So it's a bit different in nuclear reactions that you can create new elements versus what we learned in our chemical reactions. Radioactivity is the spontaneous change of an atomic nucleus. So here I have over on the right, here's a nucleus, and again, my nucleus contains my protons and neutrons. The red balls here represent the protons, the gray ones are the neutrons. So in the nucleus, we're actually changing we're giving off, in this example, an alpha particle, which is comprised of protons and neutrons. And when we give off this piece of radiation, the nucleus is actually changing. So in this one here, this nucleus, we actually have less protons and neutrons than what we originally started with. And by changing our number of protons, that changes the identity of our element, because again, our number of protons let us know what element that we have. In 1896, a French scientist named Henri Becquerel discovered radiation, and how he discovered it is he had put a rock that was containing uranium on top of a photographic plate, and it was exposed. So here's an example of our picture here. So here's his desk, and this drawer has his photographic plates in it. And photographic plates have metal plates covering film used in photography that protect it from the sunlight, which has radiation that would actually expose the film. So he has this rock sitting on the top here that contain uranium, and uranium, as we said, is a radioactive element. And what he found is he had a key in his first drawer here, and there was some kind of radiation that was coming from this rock that actually went through the key and then to the photographic plates. And so what happened is the radiation caused the image of the key to be shown on these plates, on the film inside the plates. So the metal plates around the film did not protect it. It was actually the radiation was much more powerful than sunlight. So that's what we now know is the radiation in nuclear chemistry that we'll be talking about. Radioactive isotopes can be used in medicine for diagnosis and treatment. Here's an example that's going to be used for treatment, primarily for cancer patients. So when someone has cancer, you may hear them going under treatment using chemotherapy, which is actually just means chemical treatment. So your patient would be getting some type of chemical to kill the cancer cells, or radiation therapy. And so that's what we're looking in this example here. So in radiation therapy, they're exposed to a radioactive isotope. So in this example, this is something commonly used to treat cancer, is cobalt-60. So this is a radioactive isotope of cobalt. And what they do is, depending on where the cancer is rapidly dividing cells, that the device here might contain the cobalt-60, whatever the radioactive isotope, and then that's pointed at where the source of the cancer is, so that the radiation attacks those rapidly dividing cells and kills them. So that's one way that they can treat cancer, is by actually killing those rapidly dividing cells. Unfortunately, it may kill some other cells in the area nearby, which you have to look at what's the risk-benefit factor of getting rid of the cancer versus killing a few of other cells as well. This chart shows a number of different radioactive isotopes that are used in medicine, that may be used again for either treatment, as we saw with the cobalt-60, or for possibly diagnosis, which we'll look at an example of an isotope used for that. In this example, we're going to look at a radioactive isotope used in medicine for diagnosis. We're going to look at iodine-131. Is a radioactive isotope that used to diagnose if you have any problems with your thyroid. So basically, your thyroid is located in your neck area, and the thyroid gland stores iodine and makes thyroid hormone, which is used to control your metabolism rate. So what they can do is they could administer by IV, intravenously inject a solution that contains iodine-131, which is a radioactive isotope. And then your thyroid will absorb that iodine-131. And normally, if your thyroid is operating properly, it absorbs about 12% of the iodine-131 that's administered. But you can determine if your thyroid is overactive or underactive if it absorbs more or less of the iodine-131. So what they can do is they'd actually put an instrument near your thyroid that can detect radiation. So they can detect the amount of radiation coming from your thyroid from the iodine-131 to determine if you're absorbing more or less iodine than you can normally absorb. So this is one way you can determine if your thyroid is operating properly. The other thing that's sort of interesting with iodine-131 is it is one of the components, and it says here nuclear fallout. So for example, if we had a nuclear bomb that was, exploded, or a nuclear power plant that exploded, one of the components is this radioactive iodine. And exposure to it could cause thyroid cancer. We're going to look at that in our next example. In 1986, there was a nuclear reactor that basically overheated and exploded in the Ukraine in Chernobyl. This map is showing you where the Ukraine is located in Europe, and then Chernobyl within the Ukraine. So when it exploded, it gave off this radioactive iodine that was emitted, and a lot of people ended up developing cancer from it. So this picture is showing us the reactor, what it looks like after it basically exploded. And this is showing us also that there were 31 firefighters that were killed when they came to kind of help with the cleanup there. And 6,000 people in just a 30-kilometer radius from the site developed thyroid cancer. And that was from absorbing that radioactive iodine. This picture is showing the containment structure that they built over the site at Chernobyl after the reactor exploded. So before this, they did not have a containment structure. So in the United States, you may have seen domes that show you where nuclear power plants are inside of them, basically. If you think of, for example, maybe San Onofre down in Southern California, it's no longer operational, but you'd see those concrete domes, and then the nuclear reactors are actually inside the domes. Chernobyl was such a huge disaster because there was no containment, and that's why the radiation was able to spread so far. So we said a number of people died in the vicinity, but they detected the radiation for miles across Europe as well. So this is showing the the building of the containment structure they were using to contain the radiation. This is the construction in 2012. This containment is now completed. But just to give you an idea of how large the containment area they built is, it's the length of a football field and the height of the Statue of Liberty. So that's huge. So even now, the radiation inside this area is still very high levels. I've seen specials on PBS where they show robots working inside of it, and they're detecting the radiation levels, and it's still extremely high. So again, one of the radioactive isotopes here was from iodine that was released. And I remember in 9/11 that they were talking about telling people to take iodine pills. And the idea was if your thyroid, let's pretend this is your thyroid gland, if it's saturated with iodine that's not radioactive, then you would not be able to absorb any of the radioactive isotope of iodine, hence preventing you from developing cancer. So this came out after 9/11 because they were concerned that people would be dropping nuclear bombs on the United States. So they were telling people to take iodine pills, so that way you could not absorb any of the radioactive iodine.